Very good. Bye, Luke.
How's it going, everybody? Thanks, Rami. So today I really want to give you as many examples of the process of simplifying and verifying trigonometric identities as I can, just to give you the process. The first thing that we need to know, and we need to have memorized, they will not be provided, would be the identities that we are permitted to use. And that would be the Pythagorean identities, the relationship between tangent and sine and cosine and vice versa, and I should probably leave them up as I go so that I can point to them. So I will. We have the inverse identities, which you use very often. And something I'm going to talk about in class later today, but before you've watched this video, and that is the even and odd identities. Sine is an even function. I'm going to go into more detail today in class. But sine is an even function, meaning that, is an odd function, sorry. Meaning that if you plug in an argument of the opposite sign, you output the opposite sign. So sine of negative x is equal to negative sine of x. For example, sine of pi over 3 is the opposite sign as sine of negative pi over 3. But for all x, that's true. Cosine is an even function. And that means that if you plug in a number of the opposite sign into cosine, you will output the same value. And then I think we did also say that tangent is an odd function and cotangent is an odd function. And I'll leave those up, like I said. All right. I want to do one or two of those where I can, and so I wanted to mention them. We will get to them in class. All right, so I'm going to work on the evens. Cosine of t, cosecant of t. Number 2, cosine of t times cosecant of t. And this just says to simplify, so I'll start with an equal sign. Is equal to cosine of t times, using this identity, 1 over sine of t. Pretty much almost completely across the board, if you have a cosecant, secant, something like that, that is not squared, all you're going to do, hello, Dr. Glenn.
Hello, class.
Is just make a substitution and turn it into sines and cosines. And then we want to know that this is cosine over 1. And so when I multiply across, I get cosine of t over sine of t. And just by the identity, the definition of cotangent, that is equal to cotangent of t. Jump around. I think 8 cosine squared times 1 plus tangent squared. Cosine of theta squared, I should say. 1 plus tangent squared of theta. You'll get more familiar with that. That should be pretty recognizable. Sometimes it comes up in the middle of your simplification, but if it starts there, I'm immediately identifying that as secant squared. Cosine squared of theta with a substitution times secant squared of theta. That's over there on the left. And I would want to make that substitution before I think about tangent in terms of sine and cosine. Like I said, when you don't have a square in cosecant, secant, tangent, or cotangent, then you'll probably substitute in terms of sine and cosine. And I say probably. Now, you cannot speak very easily in absolutes in this type of problem, but there are helpful ways to start, and there are probable things that could help. All right, so now I have secant squared, and I've already substituted. So now I could get this in terms of sines and cosines. Well, secant squared is 1 over cosine squared. And that should make sense, because secant is 1 over cosine of theta, Right? And then again, we have cosine squared of theta over cosine squared of theta. Begin to see that this is in the numerator, and that obviously this is in the denominator. Begin to see that a single factor by itself with no denominator is automatically in the numerator, and that's equal to 1. Who would have known? Doesn't look like 1. I think I got to do 10. I feel like I got to do 10. Cotangent of theta over cosecant of theta minus sine of theta. Don't see any squares. Don't think that I should multiply this by some kind of a conjugate with the opposite side sign. Immediately, a helpful thing to do would be to convert everything into sines and cosines. So cotangent, which is in the numerator of this fraction, is equal to its own fraction, which is a cosine of theta over sine of theta. And then in place, cosecant of theta is equal to 1 over sine of theta, and there's not as much to do with the sine. Now, I have a compound fraction. Even in rational expressions and even in algebra, we might want to eliminate these denominators by multiplying them by something. And so I'm only allowed to do things to an expression in simplification or verifying that do not change the value of that expression. Sine of theta over sine of theta is equal to 1 for all values except for 0. But we're not worried about the domain. This is equal to 1. And if I multiply on the numerator, sine of theta times cosine of theta over sine of theta, we see that these would cancel out or divide to 1. So we're multiplying by what is really the common denominator of all the fractions inside this complex fraction, with the goal of canceling out their denominators. These are the same, and so I can definitely accomplish that with sine. But it needs to be 1 that I'm multiplying, sine over sine. So now that fraction turns into cosine of theta. And similarly, when I distribute this sine of theta on the denominator when I multiply across onto these two terms, the sine in the first term cancels out, and this becomes sine squared of theta. Very helpful simplification. There is no need to try to get a common denominator here and do keep, change, flip, although it would give you a similar answer. You really want to look for this as a method of simplifying a complex fraction and turning it into just a regular old fraction. So again, I mentioned that this is the basic or the standard identity, but any simple algebraic rearrangement can be used as well. So I see that I could get 1 minus sine squared by subtracting sine squared from both sides of this identity, the Pythagorean identity. And so because of that, 1 minus sine squared of theta is equal to cosine squared of theta. Yes, it's an x in the identity, but the variable is not going to change the identity. Normally, I try to work vertically down. I really should make that very clear, because in your work, and especially on the quiz, your answer is the proof. Your answer is the demonstration unambiguously of why this expression originally is equivalent to our final answer. And you are demonstrating it to someone who may not have concluded that themselves. So there is no skipping steps. Reasonable algebraic simplifications can be made. And if it's very clear from your work that that's what you did, that's fine. But your answer is going to be, in a verifying problem, that two sides are equal. That's the final answer no matter what, or you're incorrect. And so you have to be demonstrating, and one of the best ways to clearly demonstrate is to work vertically down to the point where I'll change the place I wrote that, and I will write cosine of theta over 1 minus sine squared of, over cosine squared of theta. Yes, it takes up a little bit more room, but that's okay. I will move to the top just to not write multiple equal signs next to each other. So imagine that we were working vertically down. We have now, well, okay, I'll show you here. Cosine of theta over cosine squared of theta is equal to 1 over cosine of theta. Right? One of the cosines in the numerator and denominator each cancel. And that is equal to secant of theta. There's a similar problem right next to it, 9, and so you'll be doing that one. That's why I'm doing the evens. It'll complement pretty well. Okay. Yeah, there's a couple of good ones in a row. Again, I'm going to keep working forward with the evens. Cosine cubed of x. I don't think I've shown enough factoring yet. Sine squared of x, cosine of x. And we're just simplifying. It's not set equal to something in particular. So I see these exponents and I immediately think of the Pythagorean identity. But the exponents don't match the Pythagorean identity completely, at least not for cosine. But we know that if you factor something out, and cosine is a quantity, it is not particularly different from having x cubed and a factor of x right here. It can be factored out because it is a common factor, the function of cosine. And so if I factored that out, I would be dividing, whoa, put your x's in there. I would be dividing each term in the original expression by cosine of x. And again, if that's not clear enough, the factoring aspect, if I were to distribute this cosine back in, I would get what I originally had. And that's the definition of factoring, turning something into an expression, which if multiplied, would be equivalent to your original expression. So I'm allowed to factor out a cosine like I would be allowed to factor out an x or an x squared. I do that because, like I said, I was somewhat close to the Pythagorean identity, and I know that that is equal to 1. I'll make that very clear. You don't need to always write this. I would understand if you had this written, and then next in the multiplication, it was gone. But it's equal to 1. And so our final answer is that our original expression is equal to cosine. We'll start small with number 14 as far as the new identities, which are the even and odd identities. Secant goes with cosine. Let me make sure I'm right here. Oh, I didn't write them. Okay, that's fine. Maybe I shouldn't need to, but I'll add them. Secant goes with cosine. As in it is equal to 1 over cosine, so it has the same sign. That would make secant an even function just like cosine, which means that when I plug in a negative, it's equal to the sign of if you plugged in a positive, or the opposite sign. The opposite sign of the value being plugged in. When you plug something in with the opposite sign, the same value comes out. For cosecant, because sine is an odd function, cosecant is an odd function. Okay, so this one has tan of x over secant of x over secant of negative x. Well, we have an identity for that. We want to think about whether it's even or odd. For example, like I said, secant of, should it be in radians? Yeah. Secant of negative pi over 3, we're in quadrant 4. Secant of positive pi over 3, we're in quadrant 1. And so we know that they have the same reference angle, so the value is the same. But secant and cosine are both positive there, so they're equal to each other. That's what I mean by an even function. And that's why right here, I could say that regardless of what the value of x is, it will be true that both angles will be in quadrants that are the same sign. And so I can directly turn this secant of negative x into secant of x. Then I should put in terms of sines and cosines to simplify further. Sine of x over cosine of x over 1 over cosine of x. I don't recommend trying to cancel things out in fraction form like this. It is true that if they're both in the denominator, they can cancel out, or both in the numerator. But that becomes clearer to see when you rewrite it as a multiplication, as a product. Keep, change, flip. Right? There is a numerator fraction, there is a denominator fraction, and this is not cross-multiplying. It could be called cross-canceling, but either way, the numerator would be sine cosine over cosine. So, nope, write vertically down. Sine of x. All right, let's get to a verifying an identity. The techniques that I'm using in simplification are the same techniques that you use in verifying, so we really haven't been ignoring that completely yet. Secant cosine of v over secant of v sine of v equals cosecant of v minus sine of v. I see. I think I'm going to work with the right side. Cosine of v I see. We're going to need to do a little bit to both, but I want to work with the right side first. Made that in terms of sine. I need a common denominator. I'll multiply by sine of v over sine of v. And I get, if I may skip that singular step, sine of v times sine of v over sine of v is sine squared over v. But now that I have a common denominator, they can be combined. And that's equal to now cosine squared of v over sine of v. Looking at the left side, I see the sine of v and I see one of the cosines of v. And so one really helpful thing is to think about which portion of one side of the equation is equivalent already to a portion of the left, or on the other side, I mean. Because if I know that I already have cosine and sine, then I'm thinking this here must be where I get my other cosine on the left, which is why I would start working with the left just to get them both equal. You are allowed to manipulate both sides. Just substituting. Already I could see that having the cosine in the denominator of this part of the fraction, the denominator of the overall fraction, with keep, change, flip, you can keep this sign here. You got to be careful with the way you're thinking about that algebra, but I am dividing by cosine of v. So just taking care of that aspect of keep, change, flip, this 1 over cosine multiplies up to the numerator. I've kept the other two parts of the fraction the same. This 1 over cosine goes to the denominator, even if you think about it as a negative exponent, maybe. And so I get cosine squared of v over sine of v, which is equal to cosine squared of v over sine of v. That might need to be it. If I need to record anything more, I will tomorrow, but I think that's pretty good for now. That should be a good start. All right, I got to figure out how to end this myself. I don't normally. Oh, I was told, oh no, I did go below the line. Well, that's okay. Sorry for not showing that. But here are the identities. They are also in your textbook, so that's not so bad.